With great autonomy comes great responsibility. And that means that robots like Baxter need to first and foremost do no harm to humans or to themselves. It also helps too if they can act intelligently in the process to do their jobs. Let's watch Baxter do its job here. Excellent. I like my robots to be intelligent. In the case of Baxter, its maker, Rethink Robotics, calls it the world's first robot with common sense. Baxter's common sense starts with sensors. Right now, as it's operating, it has 4 sensors in its wrist that can tell when it's actually picked up a cup. If it drops a cup, it's aware of this as well. So it's got in each joint sensors that allow it to know position and velocity in each of its arms and each of its joints here. So this gives it an incredible ability to repeat its motions and, when we train it, to learn how we want it to move. So each of Baxter's hands also has a 3-axis accelerometer that's located in the cuff. It's in the same plane as the electrical grippers that you see operating here. So each sensor gives Baxter a piece of intelligence. And how does that work? Well, you can think of a sensor as being in charge of answering a question for the robot. The camera on the wrist, let me show you here. The camera on the wrist asks the question, where is the object on the table? Now, in this particular task, which is called a pick and place task, it's actually doing it blind. It's not using the camera. But we can do a pick and place task where Baxter will actually use that camera. There are 4 sensors that know when these fingers have hit something, okay? So Baxter has loaded with this kind of intelligence. It can ask questions like, am I picking up an object? Have I just dropped an object? Is the object here or is the object there? Let's get Baxter going again here. There we go. All right, getting it back to work. Here we go. Baxter is on the job. Now, one of the great things about Baxter is, in terms of doing no harm, it can't hurt me, right? Oh, it wants to do its job, but it's going to stop moving if it senses that I'm present. Sensors answer all our questions. A sensor is any device or mechanism that registers something happening in the world and converts that event into a signal that can be transmitted to other parts of the robot. Sensors respond to many different kinds of events, everything from changes in light to the presence of dangerous gases. In this day and age of electronic systems, sensors convert the response into a common currency, an electrical signal that the robot's computer can read. For robots, sensors determine what you know about the world. The best way to explain how sensors work is to show you. Because the common currency of sensors is electricity, we can look at how sensors change the resistance, currents, or voltage in an electrical circuit. And let's look at a bunch of sensors here. We have photoresistors that are sensitive to light. And let me show you one of those. Here is a close-up of a photoresistor on this circuit board, right here. We have switches that can act as a touch sensor. This is a giant switch. This is a classic sort of telegraph switch that acts as a sensor. We have things like a ping sensor, which is a rangefinder that can figure out how far away an object is. We have another kind of rangefinder, which is an IR proximity detector. A potentiometer, right here, is a variable resistor that can be used to signal rotational position. And keep in mind that something like a potentiometer is used in a servo motor, part of the feedback system, to allow for that motor to achieve precise control of its motion. We have accelerometers, and right here I have an accelerometer which can convert mechanical vibrations caused by acceleration into an electrical signal. And they actually work by having tiny micro electromechanical accelerometers, things that are common in our smartphones and in our robots, and they work by converting the deflections of tiny cantilevered beams with a mass at the end into a change in electrical voltage. Cantilevers can also be of a larger size, like this beautiful baby that I made and I'm very proud of. This is a force transducer. And when you hang on to one end and then you hang a weight off the other end, it generates a change in resistance that can be converted to a change in voltage that can be measured. The way that this force sensor works is this is a foil strain gauge that is actually glued onto the face of this aluminum. I've got silicon on the top to keep it waterproofed. Now, that is so tightly adhered, that resistor, that if you were to take this beam and do this, the tiny little microstrain that occurs when I attempt to bend this beam, even though we can't see that bending, would actually cause a change in the resistance of that sensor, and we can pick that up as force. So we see sensors like this in the arms of Baxter and in bathroom scales and things like that. Now, what else do we have? We have microphones, which take sound pressure waves, convert it into electricity. And it does this by vibrating a membrane that's inside, which oscillates a small magnet that induces a change in an electromagnetic field. Now, we also have, and we've got our Arduino robot as an example of this, we've got on some robots a little compass, a digital compass. Now, a digital compass is a tiny magnetometer that is sensitive to the Earth's magnetic dipole and converts that field that wraps the whole Earth into an orientation relative to magnetic north. So on the screen right here, we have a desired heading that the robot is trying to navigate towards, and there's an actual heading measured relative to that magnetic north. So this robot can actually navigate using a compass. So over here, we have a photoresistor. I've already showed you one, but I'm going to show you one in action. These photoresistors are also called light-dependent resistors because they change their resistance based on how much light is falling on them. I'm going to turn on this device, which was created by my colleague Larry Doe at Vassar College, and we'll talk about what it's doing here. It's flapping a toy fish. What's really pretty is there's a mechanical linkage under here, and I can just tilt this back and show you that mechanical linkage. There's a mechanical linkage that converts a DC geared motor's motion into this cranking action here. Now, where does the light sensor come into play? This photoresistor actually controls what would be the equivalent of turning on this device. So if I put my hand in front of the photoresistor and block the light, you can see this whole device turns, and I remove my hand like so. So this is a great example, and it all is up here in this simple circuit. This is a great example of hooking up a very simple sensor like a photoresistor to an actuator to get sensor-guided movement. I'm going to do the same thing in a simple circuit that I have right here as well. This is a little clearer to see where that photoresistor is. And the circuit includes, let me point this at this with this piece of wire. There's a transistor which acts as a switch, and a fixed resistor, and our variable resistor that we call a light-dependent resistor. I'm going to hook up some power here to this system. And what we're going to see on this DC motor is that little flag that's on there is going to spin. So you can hear and see that change. And that change is based solely on how much light is falling on that photoresistor. So that's a great example of a really annoying little device there with that noise. But that's a great example of how to hook up a sensor through a simple circuit into a motor and actually control the behavior of that motor. Okay, so we have our photoresistors here. Let's see, what other kinds of resistors do we have? We have a whole bunch of simple switches. Switches turn out to be contacts that are made that create an electrical circuit. This is a beautiful old knife switch that my friend and colleague Larry Doe has loaned me. And you can see right away what happens when you connect a circuit. These pieces of metal connect to these pieces of metal, and imagine wires coming out on either side. That completes an electrical circuit. So we know about switches from things like flashlights, okay? And I've actually had my colleague Carl Birchie cut away this flashlight for us so we can see inside here. Here's a connection for a battery, and what this switch does is it actually moves a piece of metal that contacts this upper part of this light source here. So we have simple mechanical switches in lights. We talked about this telegraph button here, and this is a classic toggle switch. And you can see we would wire in the circuitry below here, and by turning this one way or another, we'd either complete the circuit or disrupt that circuit. We can put switches into action in robots as well. This is a robot that's called TootBot. TootBot is so called because it's short for tutorial robot. And if you're interested in the circuit, this is made available by Jerry Jones from his work on robotics. And what we have here, again, is energy supply. We have a simple circuit, and I'm going to turn this on now. I'm just going to show you what's happening here. Without anything happening, we have the wheels moving the vehicle forward. Now watch what happens when I hit this little button up here. So I'll do it really quickly here on the tabletop. TootBot moves back when you hit that little button. Okay, I'm going to turn that off because that's kind of annoying too, making all that noise. What these little buttons are is they're very simple little switches. When we throw that switch in what's essentially a bump sensor, what happens is that causes relays that are in this circuit to change the direction that current is flowing through the motors. So when we change the direction of the current with that simple switch, the direction of the wheels reverses. And that gives us this backup motion. And if we had room to show you TootBot, what you would see is it would back up, one of the wheels would turn off sooner than the other one, and it would tilt, and we could have wall-following behavior, which we've seen in some of our other robots. The difference in how long each of those wheels actually keeps moving depends on the energy that goes into these two devices, which are called capacitors. That's just a neat part of our circuit. And capacitors act as temporary batteries. All right, so that's what we can do with switches. So we tend to see a lot of switches in robots. Okay, so we've also seen switches working in sophisticated robots like Roomba. And Roomba works in a much more sophisticated way than what we see in TootBot. In fact, Roomba is actually sensitive to where on its bumper you hit it, so it can change direction depending on which side you're hitting it on. So Roomba also has a number of other sensors that are very much like this IR sensor that we talked about. It's got an array of them on its front bumper. So when it approaches a wall, it can actually kick in an avoidance behavior. So Roomba is in action when it's using this kind of sensory system to go through legs of tables and things like that without having to bump them. Okay. I want to show you another kind of sensor called a ping sensor. It's an active sensor. One side sends out a signal, and the other side is waiting for that signal to return. The signal is actually ultrasound. We can't hear it, okay? And so it's coming out and coming back at the speed of sound. This robot, Sparky, has a ping sensor right up here, what kind of looks like its eyes that you see here. I'm going to turn Sparky on. Sparky is set up to be having the ping sensor, which is really an ultrasonic range sensor, send out a signal. And since Sparky doesn't have a front bumper, what we're going to see here is I tilt Sparky down. The range sensor goes red, Sparky backs up. I'll show you that in a second. I'm going to have to set him up like this. Goes forward. Sparky has this manipulator up front, so it doesn't want a bumper. And so there, it detected my hand. It backed up, so it has a virtual bumper. Sparky is never going to run into anything using its ping sensor. You can also use a rangefinder to figure out how far away something is. So they're very useful. And I want to talk about them in the same way that we've talked about these IR sensors before. These IR range sensors also send out a signal. This is light. And they're not looking at the speed at which it comes back, but they're looking at the intensity at which the light is reflected back. Both of these sensors are active sensors. They both emit energy and wait for that energy to return and figure out something about the world based on that. Now that's quite different than the photoresistor that we talked about. The photoresistor is a passive sensor. It is not emitting energy at all. So that's a basic fundamental dichotomy in the way that sensors work. They're either passive or they're active. So that's really important when we think about how to use sensors in designing robots here. So I want to show you another really cool implementation of an IR sensor. This is from Hexbug. They call it a larva. And out in front, this larva has an IR sensor. Watch how it uses this IR sensor. Now here, it's easier to show here. It never touches me, thank goodness. It's kind of creepy looking. And it uses the IR sensor to, without having to hit anything, know that it's about to hit something, and then it backs up. Another implementation by Hexbug of sensors includes this Hexbug Original, which has two passive sensors. It's got a touch sensor, which is basically a switch on its antennae here, and then it has, in the back, a microphone, which causes backup. So we've got in Hexbugs great examples of passive sensors and active sensors. You know, these are really cool robots. We've got active, passive sensors. They do a lot of things with it. I love the compass navigation, but we're missing something. We're missing vision. Vision is something that as humans and mammals, we rely heavily upon. So where does that fit in with robotics and sensors? Here is a camera that's built to be part of a robot system. We've used these cameras before to do things like detect objects. Now you have to, when you detect an object, be very careful that you color that object. And what you usually do is you look for color blobs that are unique in that particular environment. And in fact, that's how Baxter works when we use Baxter's vision to detect objects. So let's go back here and revisit our buddy, Baxter. So we had talked about Baxter's sensors that are in the joints. Baxter also has cameras and ultrasonic ping sensors. Let's talk about the cameras first. I'm going to grab Baxter's wrist and I'm going to ask it to do what we're going to call a new task. And I'm going to hit the action button here. And then I'm going to select landmark. And what landmark does, here I'm going to move Baxter's screen around so that you can see what's happening, is Baxter has turned on a camera that's in its wrist. Isn't that just the weirdest thing to say? I'm going to look through my wrist. So you can see here that Baxter's actually looking down at my feet here in the floor. You can actually see, if I put my hand here, you can actually see the two fingers that are part of Baxter's manipulator. So the idea with this camera in Baxter is that you can use things like color detection to figure out if you're looking at an object that you want to pick up. So this is great. It allows for a very flexible kind of pick and place that's not a blind pick and place, but that's actually active sensing using camera as your visual system, as your sensory system. So cameras are very useful, but they're also very difficult and require a lot of processing in order to work. And that's really shown here. When you look at this camera, look at all the electronics behind this camera to make it work. There's a lot of processing that has to go on in order to do something simple like detect color blobs and use them. Now, when we start thinking about sensors, we've been talking about them as though they exist as individual sensors. We had looked at the bump sensor here in TootBot, and we'd seen two switches helping us out. But there's another way to think about building sensors, and that is as arrays of sensors. And this is a device that my colleague Larry Doe built, which is actually using an array of emitters and a single sensor to build what's approximately an IR rangefinder. So each of these are LEDs that are emitting infrared light. In the middle is an infrared receiver, and that's covered up by black, so it's not affected by the light that's being emitted here. So this array of sensors and emitters is a way to build from scratch a combination of devices to give us range finding. Now we can also use the same principle. So this is a less pretty device, so clearly I built it. I don't have Larry's skill here. With help from my friend Bob Suter, I built a device called an IR tachometer. What's very common in robotics is we want to do things like keep track of how many times a wheel has been revolving. Let me pick up one of our wheeled robots to explain why that's an important thing to understand. So when a wheel is moving, if we keep track of how many revolutions it's made, if we can sense that motion, we can figure out, by knowing the size of the wheel, what the speed of that robot is. If you know speed and the time that a robot's been going at that speed, the product of the two allow you to calculate the distance that you've covered. This is going to be really critical when we talk about navigation of robots. And it's the essence of a kind of navigation that we call dead reckoning. So sensors and tachometers help us figure that out. So a tachometer counts the number of times something like a wheel has made revolutions. So what we do here is we have, just like you saw on that other device, we have an IR emitter, an LED, and a receiver. And what we're doing is we're having them talk right to each other. And if you can imagine the spoke of a wheel that is breaking through here, that's not a good example because that's too far away. Let me push these a little further away. So if you can imagine the spoke of a wheel coming through here, once a revolution, we would see a little change in signal that we could detect, and that would allow us to keep track of wheel revolutions. Another type of sensor makes use of the Hall effect, which was first discovered in 1879. And the Hall effect is a sideways disruption of the flow of electrical current. That disruption may be caused by a magnet, and it creates a change in voltage that can be detected and measured by a Hall effect sensor, thank goodness. By careful placement of magnets, Hall effect sensors can be used to measure electrical current flow, as well as the position and velocity of motors and other moving parts. So you can use them in the same way to count wheel revolutions. So we can really understand the importance of sensors if we think about what life is like for any robot without sensors at all. The first factory robots had none, by the way. They were robotic manipulators, arms that would go through the motions with very high speed and accuracy, but without having any feedback at all. See no evil, hear no evil. Imagine how this would be. I'll move my arm here, open my fingers, move down 2 centimeters and pick something up, close my fingers, lift my arm, rotate shoulder and here, open my fingers, over and over. This works wonderfully if you want to have a conveyor belt that's always putting something there for me to pick up and place somewhere else. But if you wanted to play a trick on me, like my sisters, you could always move the world, right, and make sure there was never an object near. So I'm always trying to pick something up, but I never did any work, and I would never know it. All my efforts would be for naught. So just to make clear, that kind of movement without sensing is not intelligent in the way that we're talking about it with modern robotics. Baxter, by the way, avoids having this problem by having force sensors in its fingers. It can tell if it's holding something or has dropped something. Now, let's think about a counterexample. All sensing and no movement. Is there such a thing? Yes, it's called a weather buoy, and they are located in the ocean. That's one such device without any actuation and just sensors. Now, a weather buoy that's floating on the surface of the water carries a variety of sensors. It has an anemometer on the tip of the pole that measures the speed of the wind. That same sensor can measure the direction of wind using a weather vane. The buoy can also be outfitted with sensors to measure the temperature of the air and the water, barometric pressure, humidity, wave action, currents, water chemistry, environmental factors, and pollution. This weather buoy may be floating freely or it can be tethered, and the solar panels charge onboard batteries that power those sensors, its data logger, and its communication system. So the weather buoy communicates via satellite to computers on land. Now, is the weather buoy intelligent in the sense we talked about, maybe somebody like Sparky being intelligent with sensor-motor interactions? Well, we saw Sparky's response to me putting my hand in front by changing its behavior. That's really movements with a purpose, like moving and not trying to hit something. And those are the hallmarks of an intelligent robots. So robots are built to move themselves, like Sparky, or to move objects like Baxter, using the cameras to sense what it has or whether it's got something in its manipulators. So without moving itself or objects in response to sensor readings, I'm sorry, but I'd have to say that the weather buoy isn't intelligent. And to be fair, it isn't a robot either. What are you going to do? Another way to think about active sensors working is that they are actually communicating with the world. They send out a signal and wait for its return. A great example of this is what we see in a remote control unit. And most remote controls, including ones for Roomba and other robots, work on the IR system. So the same kind of emitter detector system that we have here in that tachometer device that I showed you is what's happening here in a remote control unit. So it is sending out a signal, and there's a receiver on the other end that's waiting for that signal. So for short distances, that works really well for that kind of communication. Now, the coolest example I know of using visible light for communication comes from underwater robots that operate in a swarm and rely on communication with flashing blue lights. And let me just say, I said visible light here. This is actually light that's coming out. We just can't see it. So you can actually, like Paul Revere, use flashing lights, and that's what a really nifty project called COCORO, which stands for Collective Cognitive Robotics, uses. So this is a Lily robot that you're seeing. And a Lily robot moves underwater and uses blue lights on its body to signal other Lily robots. So those other robots have sensors that can detect when blue light is on. Notice the similarity here with our homemade proximity detector that I was showing you, or a remote control. So we have a signal sent and a signal received. The difference with the Lily robots is that the sender and the receiver are on two different robots. So when we see Lily in action, what we see happening is that we're looking into a pool and we can see 7 Lily robots, 3 of which have their blue lights on. They are signaling that they have seen blue lights on in at least one other robot. The robot that got all this started is called a Jeff robot, and it's down at the bottom of the screen, underwater, below the bottommost Lily. Now what's really nifty is that a single Lily robot can communicate to a robot on the other end of the swarm by using the Lily robots that are intermediate to form a string or a chain of messengers. Isn't that cool? You can think of this as roughly the equivalent of using mountaintop fires to communicate an emergency signal or a call to arms. Or think of the chain as a bucket brigade. And what's impressive about the COCORO project is that many different types of signals can be communicated. The whole swarm of robots can learn about a local situation by watching and communicating with different patterns of visible light. So, a sensor is any device or mechanism that registers something happening in the world and converts that event into a signal that can be transmitted inside a robot and to other parts of the robot. We have two main types of sensors that we've talked about, passive and active. Passive sensors, like the cameras, are built only as receivers. Active sensors, like our IR proximity sensors, are built to send and receive, communicating with themselves, if you will, by way of echoes and reflections off the world. We can split apart the sender and receiver of active sensors, put them on different robots like we just saw with the Lily robots. Or we can put humans in the sensor loop, and then we have a communication system. For robots, the specific sensors deployed, whether single, in arrays, or of different types, determine what you can know about the world. What you do with that information, how you act in response to your sensor reading, marks the origin of intelligent behavior in robots.